So we've looked at this up here. What type of problem are we dealing with here, or what am I asking us to find when I say determine EX? That's our expected value. What's another name for that expected value? Mean. And I've got a table up here. Is that a probability distribution table? Yes. How do we know? Because if I add up all these probabilities, they need to equal 1. Is it discrete or continuous? It's discrete. How do we know it's discrete? They don't always have to add up to 1, but I've got set values, interval values, not a continuous flow. These can only be 1, 2, 3, 4, or 5. It can't be 1.1 or 1.3, 2, 4, 6, 7, 8, 4. So the laptop should not be being watched right now. I appreciate that we're doing our education perfect, but I want to get a start on this. So the first question I've got you, the first thing I want you to do is to determine the expected value of that data set. So determine the expected value. What does that little E looking thing mean? Sum of XP. Now they've got I behind X and P. It just means that you have a corresponding probability for its value. So can we please determine EX there for me? So your first line of work should look something like that. Makes sense, right? 3, why would it make sense? Because all these events are equally likely to occur, so the middle score is likely going to be our expected value. Cool? Nothing new in that. Well, what I want you to do now is we're going to apply a transformation to our x value. I'm going to show us how we deal with that. So I've asked us to determine the expected value of x squared. The y is, let's just imagine this is like a scoring system for a game. I wanted to change the rules so that every point was now worth squared its value. What would I expect to be the score in an average game? To do that, all we have to do is create a third row on our table. What do you think my third row is going to be called? X squared. What's that score going to be? 1. This score? I'll let you fill the table out. Hoping you can see the pattern from there. So all we do is apply whatever transformation is being done to the x into that last row. Yep.
Do we not have a shortcut for all those brackets? Can't we just go, what's the digit
it's a simple example, so the numbers look really nice, but if I change the probabilities or change the scores, it wouldn't be nearly as nice. So because these are all 1 on 5, they're equally likely. That's really nice, but if I had like 1 on 7, 3 on 2, also it wouldn't be 3 on 2, but you get the idea, 2 on 3.
Yeah. So this would be tech 3.
That could be, yeah. That could be both. Could be either tech 3 or tech 8. So for question 2, we should have our table filled out. We have 1, 4, 9, 16, 25. Everyone get that? And now it's exactly the same as what we had before, except we're putting in x squared. And again, that I just means that we put it with its corresponding probability. Doesn't matter in this case because all the probabilities are the same. So the working would be very similar. I should have kept with the black pen, but sorry, change pen colour. So the expected value is simply the same process for x squared. The only difference is we're going to add that row. We add up our fractions because they're all over 5. We just add the top numbers and divide them by 5. 1 plus 9 is 10, 4 plus 16 is 20, 20 plus 10, 30, 30 plus 25, 55 divided by 11. Divided by 5 is 11. Sweet. I'm going to leave you to do the last one by yourself, but again, we'll need another row. And this row won't be titled x squared, it'll be titled 2x minus 1. I'll let you go through and do that last one by yourself, and then I will talk about standard deviations.